Hi, my name is Bill Kinney, and this is the 24th video that I'm making on helping people study for Actuarial Exam 2 on Financial Math, FM. I'm doing problems from the book The Mathematics of Investment and Credit, 6th edition by Samuel Broverman. This is the first video where we're looking at a problem from Chapter 2. This problem, 2.1.6s, the S means it's an old Actuarial Exam 2 problem. It's based on an accumulated value. Find an interest rate for an annuity, which is a new kind of idea here, with two different payment amounts over different periods. This problem is a little tricky. It's our first problem dealing with annuities. Actually, compared to some of the first 5 problems, it's not as tricky as some of those. Even those problems were not labeled with an S, so they're not old exam problems. I may end up going back to those because they were pretty interesting, but they involved other ideas besides the basic idea of an annuity and its accumulated value. Here's the problem statement. To accumulate in the future 8,000 at the end of 3n years, n is unspecified, deposits in 98 are made at the end of each of the first n years. So these are regular deposits. That's an example of an annuity. Regular payments, in this case, regular deposits. Then we change the amount. For the first n years, it's a level annuity. And then for each of the end of the next 2n years, we change the amount to 196. So it's like it's a piecewise constant annuity in effect. The effective annual interest rate over the entire period of time is I. You're told that 1 plus I to the n is 2. Determine the value of I. All right, before we can try to solve this problem, we should talk about how you calculate the future value or accumulated value of a level annuity over a certain period of time. So let's imagine we've got a timeline here, and we are at time 0, and we've got n payments that are going to be made, starting, say, at time 1, of 1 each time, $1 if you will. So we've got n payments of 1 at the end of n years. What we're after is the future value at time n, or accumulated value, of the series of payments based on a certain interest rate, I. Well, how do you figure that out? That can be found by taking each one of these unit amounts and pushing it forward in time, the appropriate amount. This amount is at time n, so we don't have to push that forward in time at all. This one needs to be pushed forward in time by 1 year, so I need to multiply it by 1 plus I. 1 times 1 plus I, which of course is just 1 plus I. The value of 1 at time n minus 2 needs to get pushed forward in time by 2 years. Excuse me. So its future value is 1 times 1 plus I squared, where I again is the effective annual interest rate, etc. The first value of 1 at time 1 needs to be pushed forward in time by n minus 1 years. The last value here is 1 times 1 plus I to the n minus 1. Of course, I do not need all these extra ones in there, but for extra emphasis for this first time, I went ahead and did it. So this is the future value. It's got a special symbol in actuarial science. First of all, it's labeled with an S. Why an S, I'm not sure, but S is standing for future value here. To specify that it's n payments, actuaries typically put a little sort of upside down L here and put an n inside of it to specify that it's n payments. And if we want to emphasize the interest rate, it's traditional to put I right there. This is the future value at the time of the very last payment of this series of payments. It's called an annuity immediate. And I think the word immediate, according to what I read, stands for the fact that you are evaluating its value immediately after that last payment. Okay? So that's why it's called an annuity immediate. All right, now this is really a finite geometric series. And I don't want to rederive the formula for the sum. Let me just tell you what it equals. It equals 1 plus I to the n power minus 1 over I. Actually, I should think of this as initially here as 1 plus I minus 1 but then the 1's cancel, and I get 1 plus I to the n minus 1 over I. That is the short formula for the future value of this annuity immediate, and it's the formula that we need in this problem. Okay, you can again look up formulas about finite geometric series. The common ratio here, so to speak, is 1 plus I, and we've got n terms that we're adding with a starting value of 1. I am using the formula for the sum of a geometric series to figure out this formula right here. You can again look that up. All right. So now we come to the problem itself. Draw another number line. We've got the first n years. We are depositing 98 at the end of those first n years. And then for the next 2n years, starting at time n plus 1 and ending at time 3n, we are depositing 196. And when we accumulate all these values, we are supposed to get 8,000 and ultimately solve for I. So there are n deposits of 98. There are 2n deposits of 196. What is the future value at time n of this series of n payments of 98? Well, if it were 1 instead of 98, its future value would be s sub ni. Sometimes you don't bother putting the I, but I think for this first time I will put the I. However, these are payments of 98, so I need to multiply that by 98. So that's the future value at time n, including the last payment, so immediately after that last payment of this series of payments here. What about the payments of 196 at time 3n? Well, again, if those were payments of 1, the symbol would be S. There's 2n payments, so I'd put a 2n here, and again, the interest rate is I. But they are payments of 196, so I'll put 196 in front of that and multiply those. All right. Also, this value of the payments of 98, in the end, to time 3n is going to get pushed forward in time by 2n years. Its final future value at time 3n can be written as 98 Sn times 1 plus I to the 2n. And it's these two things that, when added together, that have to give you 8,000. Okay, so I can set the sum of those things equal to 8,000. I can also replace these s's with the appropriate expression related to this thing here. This one right here, being multiplied by the 196, there were 2n payments, so it's going to be 1 plus I to the 2n minus 1 over I. Then I have the 98. There were n of those payments, so I replace this s with 1 plus I to the n minus 1 over I. And then I also have to multiply that by 1 plus I to the 2n. This is what needs to equal 8,000. Solve for I. We need to use one more piece of information. We need to use what we're given here, that 1 plus I to the n power is 2. Therefore, this is 1 plus I to the 2n power. That's going to be 2 squared is 4. This is going to be a 2. This is going to be a 4. And so we can simplify this a bit. 4 minus 1 is 3. 3 times 196, that's going to be what? 588. 588 being 3 times 196, the 3 coming from 4 minus 1, over I. Here we've got 2 minus 1 is 1, times 4 is 4. 4 times 98, that will be 392. And then I have an I on the bottom, equals 800. Now you can solve this equation for I. It's not too hard now. We already have a common denominator there. We can add the numerators, 588 plus 392. Let's see, that'll be what, 980 over I equals 8,000. Need one more zero here. Therefore, I is going to be 980 over 8,000 980 divided by 8,000. The interest rate is 0.1225, 12.25%, and that is correct. Okay, so a lot going on there. Our first introduction to annuities. Make sure you spend time looking up the formula for the sum of a finite geometric series too, to make sure you understand where this formula comes from.